Hello and welcome. I'm Johannes Seiferth from the University of Bayreuth. Thank you for your interest in our research paper. This work has been supported by the German Ministry of Science and Education as part of the Seaside project. Offsite is a novel offline autotuning approach based on analytical performance modeling. This video will introduce the basics of Offsite. In particular, we will demonstrate how Offsite can be used to autotune parallel explicit ODE methods. Why is there a demand to autotune scientific applications such as the parallel explicit ODE methods? In general, the performance of scientific applications strongly depends on the characteristics of the targeted computing platform. This includes, for example, different processor designs, different cache architectures, and different memory latencies and memory bandwidths. As these characteristics can vary greatly between platforms, a once highly performant code version might be less performant on a new platform, or could potentially be further improved by exploiting the characteristics of a new platform, for example by using newly introduced instructions. For us as a developer, this means that we have to reevaluate and adapt our code each time we switch the platform in order to achieve highly efficient code. Done by hand, this is cumbersome. Ideally, this adaptation process can be automated using appropriate methods and tools, which help software to adapt to hardware and inputs or help to improve the performance portability. This automated adaptation process is often referred to as self-adaptation or autotuning and has been subject of the Seaside project. In the Seaside project, such self-adaptation and autotuning methods are investigated and developed for time-step-based simulation techniques. The Seaside project is a joint project of the Technical University of Chemnitz, Friedrich-Alexander University of Erlangen-Nuremberg, and the University of Bayreuth, with PIKR as associate partner. Seaside aims at providing a toolbox of different self-adaptation and autotuning tools which can help developers in optimizing and adapting their code. The figure on the left shows the tools included in the Seaside toolbox. Integrated are existing tools developed at the University of Erlangen-Nuremberg, the Liquid tool, which is a performance monitoring and benchmarking suite, and the Kernkraft tool, which can model the performance of loop kernels. Further, Seaside contains a collection of additional benchmarks, BenchSide, and a collection of search algorithms, SearchSide. Seaside supports both online and offline autotuning components, whereby both sides can communicate over a database. Onsite is an online autotuner which can help tune your application at runtime, while YaskSite and Offsite are offline autotuner that can be used to tune an application at compile time. YaskSite combines Intel's Yask framework with analytical performance modeling. Offsite will be subject of the rest of this presentation. The figure shows the general workflow of Offsite. Each Offsite run starts with a tuning scenario which the user defines using YAML description languages. The tuning scenario contains all information required to tune the application. This includes information on the pool of possible implementations and program transformations, as well as information on the targeted platform, but also application-specific data. For the studied parallel explicit ODE method application, these additional information include the ODE method, the initial value problem solved by the application, and the size of the solved ODE system. Given a tuning scenario, Offsite can handle the whole tuning workflow described in the figure automatically. First, Offsite generates optimized platform and problem-specific code for all kernels and derives all possible implementation variants from the tuning scenario. Using this information, analytical performance prediction methodology is applied to predict the performance of each of these kernels. Predictions are either obtained for a fixed ODE system size n, if specified in the tuning scenario, or for a set of relevant ODE system size determined by the kernel's working sets. Once all kernel predictions have been computed, the performance of an implementation variant can be derived by combining the predictions of its kernels and adding an estimate of its synchronization costs. Offsite automatically identifies all required communication operations from the given tuning scenario information and launches the execution of appropriate communication cost benchmarks. Once implementation variant predictions are available for all implementation variants, variants are ranked by their performance to identify the most efficient variants. For the best ranked variants, Offsite generates then optimized platform and problem-specific code that can be executed by the user. After a successful run, Offsite stores all obtained prediction and ranking data in a database. This allows to share information with online autotuning tools, but also enables to reuse already obtained data in future Offsite runs. To demonstrate how tuning scenarios are defined, we consider a specific class of explicit ODE methods called PIRK methods or parallel iterated longitudinal methods. PIRK methods can be used to solve an initial value problem by performing a series of time steps until the end of the integration interval is reached. In each time step, a new approximation y kappa plus 1 for the unknown solution y is determined by an explicit predictor-corrector process in a fixed number of substeps. Thereby, the used ODE base method determines the value of the butcher table entries A, B, and C, as well as the number of stages S and the number of corrector steps M. A possible PIRK implementation could look like this. In the first two lines, we compute the predictor step. Lines 3 to 12 compute the M corrector steps. Note that two barrier synchronizations are required per corrector step iteration, as the RHS evaluation in line 11 can potentially require as input all elements of big Y, which we compute in lines 7 and 8. After all corrector steps are computed, the next output approximation is computed in lines 13 to 16. This is only one of many possible implementation variants. For instance, we could interchange the loops of loop nest 5 to 8 and try out all possible permutations. Offsite abstracts and collects all these permutations in a so-called kernel template. Kernel templates define basic computation kernels and possible variations of that kernel enabled by program transformations. The here shown implementation, for instance, consists of 4 kernel templates. Template RHS covers the IBP evaluation in lines 1, 2 or 9, 10. The before mentioned loop kernel in line 5 is covered by template LSC. The next approximation is computed by kernel templates approx and update. By defining a processing order of kernel templates and communication points, a possible abstract skeleton of an implementation variant can be described. An actual implementation variant is derived from the skeleton by replacing its kernel templates with actual kernel code, as shown here in the example. In Yastite, kernel templates are described in the YAML format shown on the right side. The example shows the kernel template approx, which computes a part of the output approximation vector. The YAML format is tripartite. The computations entry describes the computations covered by the kernel template. Each computation has a unique identifier and covers a single line of code. Here, computation C1 covers the summation of products bi times fij. The used data structs have to be defined in the data structs entry. Entry variants contains possibly kernel variants of a kernel template. Here we consider two variants, approx ij and approx ji. For each kernel, its working sets and code are specified. The code entry defines the order of computations, the nesting of the loops, and the applied program transformation using 4 different keywords. Computations are specified by keyword comp and a computation identifier. 4 loop statements are defined using keywords loop start and loop end. The first parameter specifies the loop variable name, the second defines the number of loop iterations. The loop in line 19, for instance, runs from j equals 0 to j less than n. Further, an optional third parameter unroll can be used to mark a loop for loop unrolling during code generation. For instance, the loop in line 20 will be unrolled. Last, keyword pragma can be used to add loop-specific pragmas. Using our kernel templates, we can then assemble so-called implementation skeletons. Implementation skeletons define processing orders of kernel templates and specify which communication points are required. Here we show the implementation skeleton YAML description format on the examples of two skeletons A and F. The YAML format supports 4 keywords, the already known loop start and loop end are used to define for loops, com describes communication and synchronization operations, and kernel is used to specify an executed kernel template. Thereby, the parameter of kernel has to correspond to the name of an available kernel template. During code generation, the keyword kernel is then replaced by actual kernel code. Skeleton A corresponds to the implementation shown on slide 5. It requires 2 times m plus 2 bury operations per time step. In skeleton F, templates RHS and LC are fused into template RHS LC. This reduces the number of bury operations per time step to m plus 1. To describe a tuning scenario for the PIRK methods, we further need description formats for the ODE method and the initial value problem. On the left we see the ODE method format on the example of Rado 2A7. The format contains entries for the stages, the order, the corrector steps, as well as the budget table entries A, B and C. On the right we see the initial value problem description format on the example of IC. The components entry describes the end components of the IBP. Adjacent components that execute the same computation can be described by a single block. Thereby, the entry first denotes the first component, and size specifies the total number of adjacent components handled by that particular block. Each component entry contains a code entry. The code entry describes how the function evaluation f, or right hand side, will be substituted during the code generation. %in is thereby a placeholder for the used input vector. The constants entry defines IBP specific constants. These constants are later replaced during code generation with the actual value. IC, for example, contains a variable R for the electrical resistance, which we set to 1.0. Last input are key machine characteristics, which are described using the machine description format introduced by Kernkraft. Here shown for an Intel Haswell system. Included are information on the execution architecture, such as the number of ports or flops per cycle, information on the memory and cache hierarchy, as well as benchmark results of typical streaming benchmarks required by the prediction. Kernkraft automatically obtains these benchmark results using Liquid. Using the provided tuning scenario information, Offsite automatically generates optimized code for all kernels. Here the code generation is shown on the example of kernel approx.ji of template approx. Note that code is generated in a special format processable by the Kernkraft tool. During code generation, available properties such as known constants are exploited to further optimize the code. In the example, the known number of stages S and the ODE system size N are replaced. Further, all transformations specified in the kernel description, such as the unroll to loop I in line 20, are applied. Last, budget table coefficients are replaced if possible. For our code here, we can replace the B coefficients with its actual values. These optimizations are also relevant for the implementation variant code generation. The generated code here belongs to a variant of skeleton A, in particular to the variant that replaces its kernel marker approx in line 10 in the skeleton with the kernel code generated for approx.ji, which we have seen on the previous slide. In addition, there would be a second variant of A that would use approx.ij instead of approx.ji. For space reasons, the code generated for the remaining kernels RHS, LC and update isn't shown. Note that also the OpenMP initialization and workload distribution are not shown here. Both are handled by the driver function that calls the generated time step function. Since we know that the number of corrector steps is fixed and is here set to 6, we can replace the value during code generation. Offsite generates implementation code only for the best rated variants. To determine the performance of an implementation variant, an analytical performance model is applied. The runtime prediction of an implementation variant is composed of 2 contributions. Firstly, the node level runtime predictions of the kernels associated with the variant, and secondly, an estimate of the required inter-node communication costs used by the implementation. To obtain node-level predictions, the kernels are evaluated with the analytical ECM performance model. The communication costs are benchmarked. Assuming we solve an ODE system of size n with an implementation variant epsilon using tau threads, we can then estimate the runtime theta of epsilon as theta epsilon equals the sum of all kernel predictions phi plus the communication costs. For example, for a variant A1 of skeleton A that uses kernels RHS LJ, LC Lij, approx Ji, and up J, we would get the here shown prediction theta. How can we obtain node level prediction phi for a specific kernel lambda? Again, we assume that we solve an ODE system of size n on tau threads, then we can estimate the runtime phi of a kernel lambda as alpha lambda times b lambda divided through delta times f. Hereby delta is the number of elements fitting into one cache line and f is the used CPU frequency. Hence both are machine dependent. Alpha is the ECM model's estimation of the number of CPU cycles per cache line required to execute lambda. Beta is defined as the total number of loop iterations executed by lambda. The ECM or execution cache memory model can estimate the number of cycles per cache line required to run a loop kernel on a multi or many-core chip. At large, the model assumes that the single-core execution is composed of two contributions. The in-core execution time is defined as the time required to retire the instructions of a single loop iteration. The data transfer time factors in the time required to transfer all data from its current location in the memory hierarchy to the L1 data cache and back. The transfer time between L3 and memory is thereby estimated using the benchmarked bandwidths stored in the machine description. Offsite uses the Kernel tool, which can automatically construct the required ECM predictions. The screenshot exemplarily shows the Kernel output for kernel approx Ji. Kernel does not only give us a single core prediction of 48.17 cycles per cache line, but also provides predictions for all other core counts. Hence, Offsite has to call Kernel only once per kernel and ODE system size to get predictions for all available core counts. For validation, we studied the efficiency of Offsite and the reliability of its variant ranking on 3 different platforms when tuning different IVPs in different autotuning scenarios with different autotuning strategies. The table shows key characteristics of the used Haswell, Ivy Bridge and Skylake system. For the experiments, the CPU clock frequency was fixed to the shown value and hyperthreading disabled. The 3 systems have the same L1 cache size but different L2 and L3 cache sizes. The measured memory bandwidth required for the ECMM model prediction was benchmarked with Liquid. All codes were compiled with the Intel C compiler and flags -03, -x, AVX and F no alias Z. 4 different IVPs are considered. CASP combines Siemens CASP catastrophe model with the Van der Pol oscillator. Its ODE system is derived from 3 PDEs. The components of the first PDE are memory bound, the components of the other 2 PDEs are compute bound. Hence we call it a mixed bound problem. IC is compute bound and describes a traversing signal through a chain of concatenated inverters. Reduxo describes the penetration of radio-labeled antibodies into a tissue infected by a tumor. Its ODE system is derived from 2 PDEs, and the component of the first PDE are compute and the components of the second PDE memory bound. Wave 1D is memory bound and describes the propagation of disturbances at a fixed speed in one direction. We use a pool of 56 different implementation variants for our experiments. The shown table summarizes how implementation variants can be derived from the available kernel templates and implementation skeletons. Each column shows the templates required by a specific skeleton. For example, the earlier introduced skeleton A uses templates LC, RHS, approx and update. 12 different variants can be derived from skeleton A, as there are 6 different kernels of LC enabled by loop interchanges, unrolls and pragmas, and 2 of approx. We further include 12 different variants from B, G and H and 2 different variants from C, D, E and F. In total, 17 kernels are used to derive 56 implementation variants. To predict the performance of all 56 variants, only these 17 kernels have to be estimated, as predictions can be reused. Further, when changing the IVP, only the 6 kernels that contain evaluations of the IVP's right-hand side need to be re-evaluated to derive predictions for all 56 implementation variants. Using the introduced testbed, we studied different autotuning scenarios. For the first scenario, we assume that all input is known at installation time, in particular the ODE system size n, which we set to 36 millions. Here we do not need Offsite's working set model, as we are only interested in the prediction for a single n value. Table 4 compares the accuracy and efficiency of 3 auto-tuning strategies when tuning 4 different IVPs on Skylake. Strategy run all runs all 56 variants to identify the best variant. Off-pre5 selects the best variant from a subset of all variants. The subset contains all variants within a 5% deviation of the best ranked variant by Offsite. Off-pre10 allows a bigger deviation of 10% and might contain a bigger subset. The table shows that all Offsite strategies were able to successfully identify the best variant for all IVPs. For each IVP, a subset of 3 variants was tested, which led to a marginal tuning overhead. In comparison, run all led to significant tuning overheads for all IVPs. For the second scenario, we assume that the ODE system size is not yet known at installation time. As this requires computing multiple performance predictions per kernel, a single offsite run takes a bit longer than in the previous scenario. The figure shows on the x-axis the ODE system size n, and the y-axis shows the time per component of n in seconds required by a specific variant to solve a time step when solving IVP CAS with ODE method Raro 2i7 on Haswell. Both offsite strategies select the same subset of 3 variants independent of m. The corresponding plots for off-pre5 and off-pre10 show the runtime of the best of these 3 variants. The red plot shows the runtime of the actual best measured variant of all 56 variants. We can observe that all plots overlap, meaning that off-pre5 and off-pre10 always correctly identified the measured best variant. In the last scenario, we assume that the core count wasn't fixed beforehand. Since Offsite can predict the performance of an implementation variant for different core counts with a single Offsite run, Offsite is capable of handling such scenarios effectively. The figure shows the effectiveness of 3 different auto-tuning strategies compared to a strategy that would test all 56 available variants. The strategies include the 2 offsite strategies and a random select strategy, which randomly executes 20 variants and then selects the best of these 20 variants. The red line shows the performance gain we would achieve by already knowing the best variant and executing it instead of the 56 variants. Ideally, the bar of a strategy is close to the red line, as that indicates that the strategy selected a proper variant with marginal overhead. In the figure, we see the results for n equals 9 million, IVP-IC, ODE method Raro 2a7 on Ivy Bridge. The figure shows that we can achieve significant performance gain with either offsite strategy independent of the core count. In fact, the performance gains are close to the maximum gain of the best variant for all core counts, and in each case, the random select strategy is decisively outperformed. Last, it can be observed that the total performance gain grows with increasing number of cores. In this video, we have introduced Offsite. Offsite is able to automatically identify efficient implementation variants at installation time. Optimized implementation variant code can be generated from multi-level YAML description languages provided by Offsite. To predict the performance of the individual implementation variants, an analytical performance model based on the ECM model is applied. We tested Offsite on a representative class of parallel explicit ODE methods called PIRK methods and demonstrated that Offsite can reliably tune these codes for different auto-tuning scenarios and strategies. Thus far, Offsite is limited to shared memory systems. In our future work, we plan to extend our approach to cluster systems and plan to extend our approach to a combined offline-online auto-tuning approach that also incorporates data from the online auto-tuning. Thank you for your interest. For more information on Offsite, go to github.com/csite-project/offsite.